This is the pre-lab for the first part of a 2-week experiment involving the isolation of the acidic component of clove oil. This pre-lab will focus on the isolation of clove oil from cloves. In this experiment, we will learn how the essences of plants are obtained from plant material. In this presentation, we will cover the pre-lab assignment, safety information, the goals of this experiment, and the methods that will be used to achieve those goals, background information about the new techniques that will be used to isolate the clove oil, some specific information about conducting the experiment, and how to clean up at the end of the experiment. Your pre-lab for this experiment consists of reading the assigned sections from the Techniques in Organic Chemistry, watching the demonstration videos on extractions and drying organic liquids, and preparing your notebook using the investigative format. The safety information you need to know for this experiment is limited in its scope. Since we're working with a natural product, there is no need to wear protective clothing when handling the cloves. However, dichloromethane is a suspected carcinogen. So, whenever you're working with it, you have to work in a fume hood, and you have to wear gloves. If you get any DCM on your hands while wearing the gloves, which may very well happen in this experiment, it does have a tendency to penetrate through the gloves. You'll be fine if you simply remove the gloves, wash your hands with soap and water, and get a new pair of gloves. There is one main goal of this experiment, and that is to isolate the essential oil of cloves. You will do this using several different techniques. You will first perform a steam distillation to co-distill the oil with water. You will then extract the oil from the water using DCM. After extraction is complete, you will dry the DCM using sodium sulfate. Finally, you will evaporate the DCM from the oil using a steam bath. To understand the methods used in this experiment, we have to first understand what an azeotrope is. The definition of an azeotrope is a mixture of two liquids that boil together at the same temperature that cannot be separated by distillation. The reason this occurs is usually due to strong intermolecular interactions in the liquid state. An example of this is a mixture of water and ethanol, where the two liquids can form strong hydrogen bonds. Let's look at a composition diagram of ethanol and water for both the liquid and vapor phases, with the x-axis representing the percent of water, where the bottom line represents the liquid phase and the top line represents the vapor phase. We see the two curves come together at a particular point here. At this point, the mixture is 4.5% water and 95% ethanol. This is the azeotropic point, where the liquid and vapor are at the same concentrations, so the vapor won't be any richer than the liquid, like we saw in a fractional distillation experiment. At this stage, purification is limited by conventional distillation methods. This is why absolute ethanol is 95% or 190 proof. Now, steam distillation is a special type of azeotropic distillation, where an oil that would typically have a very high boiling point can easily be distilled as an azeotrope with water. This is typically how essences or flavor oils are isolated from plants. The key is that the azeotrope can be distilled at low temperatures, so you don't run the risk of decomposing the oil at elevated temperatures. Once the oil is azeotropically distilled, once it cools, it is fairly insoluble in water in the liquid phase. We therefore have to extract it from the water layer. Extraction is a technique used to separate a compound from a mixture. and we will specifically be using liquid-liquid extraction, where there is a distribution of a compound or solute between two solvents that are immiscible in one another. Generally, water is one of the solvents, and the other solvent is an organic solvent, which can be anything ranging from diethyl ether to hexane, as long as it is immiscible or insoluble with water. Here we will be using DCM, dichloromethane, for the experiment. In an extraction, the aqueous and organic phases are gently shaken in a separatory funnel, as depicted in the figure. We will be using the large separatory funnel for this experiment. Typically, an organic product will be suspended in water, as is our case with the oil. There may be other inorganic byproducts in the mixture as well if you're working up a reaction. The organic solvent is then added to the mixture, as you can see in Part B. Something to note is that the separatory funnel in Part B of the figure shows the organic layer on top. However, you always have to be aware of the density of the solvent. Whichever solvent is more dense will be the one on the bottom. Once the organic product has been extracted, the two layers can be separated. We've separated the organic product from the aqueous layer. The effectiveness of this separation depends on the solubility of the solute in both the aqueous layer and the organic layer. In essence, the solute will be distributed between the two layers, establishing an equilibrium. The difference in partitioning is called the distribution coefficient. This distribution coefficient, which is labeled K, is defined as the solubility of the organic solvent, the solubility of the organic compound in the particular solvent divided by the solubility of that organic compound in the same volume of water. If K is large, that means that the organic compound is much more soluble in the organic solvent, and this makes it easy to separate. However, usually K is less than 10, and in this case, to get the best recovery of the organic compound from the aqueous phase, we have to extract multiple times. Now, why do I say this? Well, we can calculate the efficiency of extraction using the following equation, where V1 is the volume of the organic solvent, V2 is the original volume of water, N is the number of extractions, and K is the distribution coefficient. Let's consider an extraction of phenol between water and hexane. The solubility of phenol and hexane is 37 grams per 100 milliliters. The solubility of phenol in water is 8.3 grams per 100 milliliters. So the distribution coefficient is the solubility in hexane divided by the solubility in water, which we see is 4.5. So, if we start with 8.3 grams of phenol in 100 milliliters of water and extract only once with 100 milliliters of hexane, we can use the equation where the initial mass of phenol is 8.3 grams, V2, the volume of water, is 100 milliliters. V1, the volume of hexane, is also 100 milliliters. The number of extractions is only 1, and of course we just calculated K to be 4.5. Solving for the final mass in the aqueous layer, we find that there is 1.5 grams of phenol still left in the water. So notice you calculate what is being left in the water, not what is being extracted into the hexane. Simply subtracting the initial amount that we started from with the amount that is still left in the water, we see that only 6.8 grams of phenol was actually extracted. Not bad, but if we perform 4 extractions, with 25 milliliters of hexane, where the total volume is still 100 milliliters, we see, after setting up the equation, there's only 0.41 grams of phenol left in the water. This means that there's 7.9 grams of phenol that has been extracted into the hexane layer. So we see that one extraction gives an 82% recovery of phenol, but 4 extractions with a total volume that is the same gets a 95% recovery. The key is that we've used the same volume. Another technique that will be utilized in this experiment involves drying an organic solvent with a drying agent. Whenever we extract a substance from water, some of the water is soluble in the organic solvent, so we have to remove that water. The most common way to dry our solvent is to add an anhydrous material. Anhydrous drying agents adsorb the water, forming hydrates, which are insoluble in the organic liquid and can be easily filtered off. Some of the more common drying agents that we will utilize most of are magnesium sulfate, sodium sulfate, calcium chloride, calcium sulfate, which is often referred to as dryrite, and in some very select cases, you can use certain compounds. For example, potassium hydroxide is used to dry amines. To dry an organic solvent, you simply add the drying agent to the solvent. You typically add roughly 1 gram per 25 milliliters of solvent. This is usually sufficient, although sometimes you'll need to add a little more or a little less. You then swirl the flask to mix the drying agent with the solvent, allowing it to react with the water that is present. The trick is knowing if you've added enough drying agent. If you see some of the drying agent moving freely as you swirl and not clumping, then you essentially have added enough. Think about a snow globe, and you will get the idea. Once the solvent is dry, you can separate the solvent from the insoluble hydrated salt by decanting the solvent into another flask. If the salt contains small particles, you can filter it off using a fluted filter paper or a plug of cotton. Here are some pointers when conducting the experiment. The first step involves weighing 25 grams of cloves. Make sure you record the amount you weigh. When you transfer the cloves to the flasks, sometimes you have a little bit difficulty with the cloves. They're fairly large pieces of material. So you can use your powder funnel to facilitate easier transfer. Once you have everything set up and distillation starts, you'll notice that the distillate should look almost like milk. Now the procedure calls for using a 25 milliliter graduated cylinder, but you can also use a 10 milliliter cylinder as well if you don't have a 25 ml cylinder. The reason why we use a small cylinder and transfer it over into the larger one is because using smaller graduated cylinders allows you to collect small samples which you can transfer to the larger 100 milliliter graduated cylinder. This is to ensure that in case there's any bumping of the cloves or foaming occurs and particulates accidentally come over in the distillation, you simply discard the small volume of distillate you've collected while keeping the majority of the distillate still intact. Also be aware that your 100 ml graduated cylinder holds about 110 milliliters of total volume. So you're going to be collecting 120 milliliters. This means that the last fraction of the roughly 10 milliliters is going to be collected in your smaller 10 ml or 25 milliliter graduated cylinder. After you've collected all your distillate, you will pour it into the larger separatory funnel. Make sure the valve is closed, otherwise you're going to be dumping it onto your bench. You then add 15 milliliters of dichloromethane to the separatory funnel, and then you stopper the funnel. Make sure you place a little grease on your stopper, otherwise it will get stuck in the funnel. Note, the DCM should be on the bottom of the funnel because it is more dense. Once the separatory funnel is closed, you need to invert it and vent quickly by opening the valve. You'll notice it hisses. If you then close the vent and you gently shake it, then you're going to vent again. The key is venting often. And at this stage, I want to give you a little warning here. If you do not vent quickly, especially in the initial mixing of the solvents, this will lead to the stopper popping out, as seen in the figure shown below. Now, if it pops out while the funnel is inverted, you're going to lose product, so be careful. Once mixing is complete, drain the bottom dichloromethane layer into an Erlenmeyer flask. And then you're simply going to repeat the first 5 steps, using fresh dichloromethane every time that you're adding into the separatory funnel. You then combine all of the DCM extracts into the same Erlenmeyer flask. After you've combined the extracts, you need to dry the dichloromethane because it contains water as well in the solution. We will be using sodium sulfate to dry the dichloromethane. Once dried, you should be able to simply decant the dichloromethane into a pre-weighed 125 ml Erlenmeyer flask. To evaporate the solvent, you place a wooden stick into the flask, and this will act like a boiling chip as the solvent boils to control any bumping. Place the flask onto one of the steam baths. The steam baths can be found in the hood, and you simply are going to turn the steam on. You can find the steam knob on the front fascia of the hood. Make sure the steam isn't coming out too strongly, otherwise your sample may boil over. You may start to sweat after some time when you see almost everything disappearing in your flask. Don't worry, you'll only be left with a small amount of oil. And once the dichloromethane has evaporated, you think that most of it is gone, you simply allow your flask to cool to room temperature. You're going to place parafilm on the top of it, and then you're going to set it in your locker for the following week. Now there are 2 stages of cleanup that I want to mention. The first stage involves cleaning up the cloves. You will want to do this directly after distillation of the clove oil. Make sure you pour out as much water down the drain as possible, and then scrape the cloves into a beaker. And that beaker is going to be found in the waste hood. It's going to be a very large beaker. It should have a plastic bag inside of it. The second stage of cleaning up is after the extraction. You'll have the hydrated sodium sulfate in a flask. Make sure you place it into the appropriate waste container since it has some residual dichloromethane in it. The aqueous layer from the extraction can be discarded down the drain. And your final step is simply to wash your glassware with soap and water and make sure you rinse very well.